Okay, in this segment we're going to be looking at a common emitter amplifier. With diode degeneration. Alright, so this is going to be similar to the one that you're looking at in the fourth experiment in Lab 3, but instead of having a resistor between the emitter and ground, we're going to actually have a diode connected transistor. So we have VCC up here. We've got a resistor R connected between the collector of our input transistor, and then we've got a second transistor down here, which is going to be diode connected, like so. Our input voltage comes in here on the base of our top transistor, and the output voltage is going to be here on the collector. So this is V out. And our goal with this is going to be to find the voltage transfer characteristic and to find the incremental gain of the circuit, which is dV out, dV in, using direct differentiation of the voltage transfer characteristic, and this will be a large signal analysis. And we're going to go back and we're going to look at also what's called a small signal or incremental analysis and try to correlate the results of these two analyses. Okay, so we're going to call these two transistors here Q1 and Q2, and we're going to assume our typical zeroth order assumptions. We're going to assume that the transistors are matched and that they are operating at the same temperature. We are going to assume that for the time being that the early effect is negligible, and we may assume that the base current is finite. So we're going to assume no early effect, and we're going to be assuming finite beta. So assumptions, matched transistors, same temp, and we're going to neglect the early effect, but beta is finite. Okay, so these are our assumptions. Well, what do we know about these transistors? Well, we know a couple things. Let's call this node voltage down here V. That's the emitter of Q1 and the collector slash base of Q2. We know a couple of things. We know from Ohm's law and Kirchhoff's current law we know something about V out. Okay, so if we knew what the collector current in Q1 was, call that IC, we could write V out as VCC minus the voltage drop across the collector resistor. Okay, this is sometimes called the load resistor. Okay, and what that resistor is doing is basically taking the current that's being generated by the input voltage and turning it back into a voltage. Okay, that's what this resistor's job is in life. It's to basically take this current, which is related to the input voltage, and turn it back into an output voltage. Okay, so that current has to flow through that resistor, and because a resistor is a linear device, that will linearly turn the current into a voltage. Okay? So that tells us that V out is going to be VCC minus IC times R. Okay, so if we know what IC is and how that relates to V in, then we can figure out directly from this equation what V out is as a function of V in. Okay, so that's one piece of the puzzle. We know that the collector current is going to be related to the emitter current through alpha. Okay, with a finite beta, we know that IC over alpha is the emitter current. And that C is not particularly visible. So IC over alpha is the emitter current. And also IC over beta would be the input current. Okay? Now this current IC over alpha is going to split up, and some of it's going to flow into the base and some of it's going to flow into the collector of Q2, right? And then those two currents are going to recombine and flow out of the emitter of Q2. And because these two transistors are matched, I would argue that this has to also be IC over alpha. Okay? So these two transistors are matched. We're going to assume also that Q1 operates in the forward active mode or soft saturation. I forgot to mention that. So we're going to assume that that's true, and then we'll go back and we'll check where that assumption becomes invalid, okay, as a check on our result. So Q1 operates in the forward active mode by assumption, and Q2 has to as well, okay? That's because it's diode connected, and it's carrying a current, and so that means it must be forward biased. And if these two devices are operating in the active mode, and there is no early effect, which is what we're assuming here, the matching assumption basically guarantees that these two transistors have basically identical base to emitter voltages. Okay, so you should be able to convince yourself of that, because in the forward active mode, the collector voltage does not affect the collector current, right? It acts like a current source with respect to the collector voltage. And so the collector to emitter voltage actually doesn't matter with respect to changing the current. It's just the base emitter voltage. And so if they're carrying the same current, then they need to have the same base emitter voltage. Okay? And certainly this emitter current will be the same as this emitter current, because no matter how these two things split inside the transistor, they recombine, and this is the emitter current of our Q2. Okay? So we can write down the forward active model for both Q1 and Q2. And for Q1, say Q1, that tells us something about the relationship between IC, namely it's IS, and Vin and V. Vn minus V, base minus the emitter, over UT. The forward active model for Q2 further implies that this is also IC, by the way. This is IC over beta. The emitter currents are the same. The transistors have the same alpha and beta. They're both in the active mode. That means that all the terminal currents should be the same. And so we can write down that the collector current here is also IS e to the VBE, which in this case is V, right, because it's the base voltage, minus 0 over UT. Well, we can divide these two equations. So let's call this 1, 2, and 3. We can divide, let's divide, or we can set them equal. Let's set them equal. So by the transitive property of equality, these are both equal to IC. We have, I guess I don't need the 2 and the 3 if we're going to do that. Well, maybe I need the 2 and the 3. I may need to go back and substitute. So those two imply that IS e to the V in minus V over UT is equal to IS e to the V over UT. Well, we can cancel the IS's, the devices match. We'd like to eliminate V, right? So we don't want to know IC as a function of V in and V. We just want to know it purely as a function of V in, so we can go back and get an expression for V out as a function of V in. Okay? So we need to eliminate V. And so we can multiply both sides by e to the V over UT, right? Because that will undo the e to the minus V in this V in expression. So take 4 times e to the V over UT. That will give us, on the left-hand side, we get e to the V in plus V over UT minus V over UT. We'll just get e to the V in. And on the right-hand side, we're going to get e to the 2V over UT, because we're multiplying both sides by e to the V. We get e to the V plus e to the V is e to the 2V. And this is really e to the V over UT quantity squared, right? So this is e to the V over UT quantity squared. We basically take the square root of both sides to eliminate that square, and we find that e to the V in over 2UT is equal to e to the V over UT by taking the square root of both sides. So 5 square root. And if you like, we can substitute this into 3. So if we call this 6, and go 6 substituted into 3. So if you recall, 3 up here gives us that IC is directly IS e to the V over UT. So we have an expression for e to the V over UT as a function of e to the V in, right? So we can just substitute the left-hand side in for e to the V over UT up here. And we get that IC is equal to IS e to the V in over 2UT. Okay, so that's 7. We substitute 7 into 1. That tells us that V out is equal to VCC minus R IS e to the V in over 2UT. And so that is our voltage transfer characteristic. Okay, so you can see that as Vin increases, Vout will decrease. And we can also take this expression and differentiate it with respect to Vn and obtain an expression for the incremental voltage gain. So A, let's call that A, is dV out, dV in. Okay, this is the slope of the tangent line to this voltage transfer curve. And that's going to be equal to, well, let's see, it's a partial derivative, so everything else is held constant except for the thing we're differentiating with respect to. So the VCC is a constant, minus RIS is a constant. E to the Vn over 2ut, we have to differentiate that with respect to Vn and apply the chain rule. So we get minus RIS. Derivative of an exponential is the same function, it's the exponential function. And we apply the chain rule and we bring down a 1 over 2ut. And so we are left with minus RIS over 2ut times E to the Vn over 2ut. Alright, so that's our voltage gain. So maybe we will capture those two things over here. Give this some space. And we'd like to sketch this voltage transfer characteristic and go back and check our assumption, or think about our assumption about the forward active model applying to our circuit, or Q1. Okay? So you remember a voltage transfer characteristic is a plot of V out versus Vn. And we'll have this box of VCC, VCC, that defines our sort of range of voltages. And let's see if I can draw the identity line here. So this is the identity line, and I really probably wanted to make that a dashed line. Equals Vn with a slope of 1. And so for low values of Vn, this is going to be very small. So Is is a number like femtoamps, and if R which might typically be, oh, I don't know, kiloohm or something like that, we're going to have very, very small currents here. E to the something like 0 will be 1. So we're going to have very, very small voltage drop across our load resistor, and we're going to just be up at VCC. And that's going to persist for a while. So the characteristic is going to be very flat up here, very close to VCC. Meanwhile, this current, as we increase V in, is exponentially rising. Okay, it's not rising at a rate of 60 millivolts per decade, but it's rising at half that slope, and so it's going to be 120 millivolts per decade. But after a few 120 millivolt increases in the voltage, this current will very rapidly approach a milliamp. It doesn't take too many orders of magnitude to get from a femtoamp up to a milliamp, right? And so within a couple of volts, what's going to happen is that this is going to take off, and it's going to look like it's just going to peel down very rapidly at an increasing rate because it's an exponential. Okay? And then at some point, this device, Q1, will leave the active mode, right? So it will leave the forward active region. And so Q1, for Q1 to be active, we need to have V out, which is the collector, has to be higher than, greater than or equal to the base, which is V in, right? So the collector has to be at least as high as the base for Q1 to be active. Okay, so when does Q1 leave the active region? Well, V out is greater than V in when this curve is above this identity line. Okay, so Q1 leaves forward active region right there. So Q1 is in the active region pretty much this whole time. At Vn equals 0, Q1 will not be, strictly speaking, in the active mode because Vn equals 0, V will also be 0. It can't be less than 0, and it's not going to really be, if it's above 0, then my argument here gets stronger. But when Vn is equal to V is equal to 0, we have both the collector base junction being reverse biased and the base emitter junction being reverse biased. And so both junctions being reverse biased means the device is formally in the cutoff region. So Q1 is cut off at that one point. So at this one point, Q1 is cut off. Q1 is in the forward active mode all through this part of the curve. And then we have to think about where does Q1 leave the soft saturation region. So for Q1 to be in soft saturation, we need that the collector V in will be less than V out, so V out is below V in, and greater than or equal to VE, which is, in this case, we've called it just V, plus VCE sat. All right, so we need to have that the collector to emitter voltage, which would be V out minus V, is greater than or equal to VCE sat. Okay, VCE sat is about maybe 4 or 5 UT. Typical numbers would be something like 125 millivolts, maybe 150 millivolts, something like that. So it's not a very large voltage across the transistor, but you need at least that much across the transistor for it to be in soft saturation. And so we need to think about, what is V doing? Okay, so V is the emitter voltage, and we actually know what V is doing because we had that equation that said e to the V over UT was equal to e to the V in over 2 UT. right? So this implies, if we take the log of both sides and multiply both sides by ut, this implies that V is equal to Vn over 2. Okay, whatever Vn is doing, V is just half as much. Okay, you need to be a little bit careful with this result, because it may give you the impression that these are just acting like resistors, and this is like a resistive voltage divider or something like that. And this is not a resistive voltage divider. Okay, please get that out of your head. These two devices are nonlinear devices. We're not approximating them as resistors. These are highly nonlinear devices. They happen to be matched devices, and so for the same current, they need to have the same base emitter voltage. Okay, that's what's going on here. V is just half of Vn, and so we can actually plot here a line that represents what V is doing. So we know what Vn is doing. Vn is following this identity line here, and on this graph we can basically plot another dashed line here, which is V. So this is V out equals Vn over 2. So the slope of this line is 1/2. The slope of this line is 1. So this represents what V is doing. Okay? And so we can construct a line that's parallel to this line, with a slope of 1/2, where this is intersecting here on the y-axis at VCE sat. Right, so this line here would be, just draw this here, V out equals Vn over 2, and that line that's parallel to this is V out equals Vn over 2 plus VCE sat. So now when this model comes down here, it continues to go down. That's the prediction from the model, right? This is where Q1 leaves soft saturation. So Q1 is in cutoff right here at this point. It's in the forward active mode all through here. At this point where it crosses the identity line, it leaves the forward active mode, and in this little region here, it's in the soft saturation region, still behaving as if it were in the forward active mode, well described by the forward active model. And then right here, at this point, it leaves soft saturation. Okay, so this model will not describe what's going on with the actual curve, the voltage transfer characteristic, beyond this point. Okay, all bets are off. I'm not going to say what actually would happen here. You can obviously fire up LT-Spice and put the circuit in LT-Spice if you're curious to see what might happen in the circuit, but suffice it to say that this prediction from the model that this continues plummeting down here at an increasing rate is not going to be what describes the behavior of the circuit. Okay? So a couple of more things that we might be interested in comparing with our incremental analysis in the next segment for this circuit, really quickly, are the input current, so IN, which is equal to IC over beta, right? So IC was IS e to the Vn over 2 ut. Divide that by beta, that's IN. And if we wanted to know what is the incremental input resistance, right, we would say Rn, which is the incremental resistance seen here looking to the base, would be equal to, formally it's it's dVin din, which is going to be 1 over din dVn. And so we can take the derivative din dVn and find that we have Is. Again, we differentiate the exponent or exponential. We get e to the Vn over 2ut. We have a 1 over beta here. We multiply that by 1 over 2ut from the chain rule, and we get Is over 2 beta ut times e to the Vn over 2ut. And of course we could re-express this in terms of In, right, because In is just Is e to the 2 Vn over ut. So this part here is just In, and so this is equal to In over 2ut. So Rn is equal to 2ut over In. So this was In, and this is Rn. Okay, so that's all we're going to do for this segment. In the next segment we'll do an incremental analysis using the result from the packet, which tells us what is the transconductance of an emitter degenerated, or a bipolar transistor with emitter degeneration, and what is the base resistance of a transistor with emitter degeneration. Okay, we'll compare that with these results that we have here from the large signal analysis. We'll see you next time.